Hello, everyone, and welcome to the second presentation in the CP Research Seminar Series. And thank you all for joining us today, virtually and here. My name is Arzu, and I have the honor to introduce my advisor and today's presenter, Dr. Lisa Sundahl Platt. She's a researcher with Florida Institute of Built Environment Resilience, known as FIBER, focusing on public health resilience, and she's also an assistant professor of interior design with the College of Design, Construction, and Planning, University of Florida. Her graduate training includes a Master of Science in Psychology and a Ph.D. in System Science, focusing on health system engineering. Her research explores the use of AI and computational modeling to evaluate outside design basis hazards on built environment resilience. The goal of this work is to understand how complex system analysis elicits practical innovation, improving human safety and well-being.
Thank you, Arzu. Okay, so thanks all of you for being here today. Thanks for those of you who are online who can attend. So yeah, I want to talk to you today about the utility of using computational models to forecast built environment resilience. So just by a show of hands here in the room or online, how many of you are already using computational modeling or AI to further your applied work or research, or is this okay, somewhat. So this is going to be new information to some of you, and some of you this is going to seem something somewhat familiar, but hopefully I can introduce some new concepts, because when I was pursuing my PhD in engineering, I found that there were a lot of tools that aren't being used in building, construction, and design that have great potential to inform the safety and reliability of those practices. So just as a way of introducing myself, I spent about 25 years in practice, specifically focusing mostly on the design and construction of healthcare spaces, which, as we know, are safety critical environments and are relatively complex. So oftentimes, even though following best practices for design and planning, we would find at the end of the day that even following things like building codes, best industry practices, and developing solutions with the client in a very hands-on way, the end result didn't always meet the needs or the emerging needs of the client. And I say needs because needs change and expectations don't. They always met the expectations, but sometimes the needs weren't necessarily met. And so as I continued to work in the profession, I really wanted to understand specifically how this happened. Oops. And then why this happened in terms of any kind of root cause outcome that might be contributing this. So as we know, building environments that support human users are pretty complex. And so coming up with the why was the thing that led me to the concept of resilience. So Arzu, when she introduced me, indicated that I work for the Institute, the Florida Institute for Built Environment Resilience, which is an institute, the only institute embedded in the College of Design, Construction, and Planning. And we are focused on research for differing types of resilient environments. Has anybody in here, other than my two GRAs who work over there, heard of FIBER? Okay, so yeah, one of you has. So FIBER is really committed to this whole notion of how do we develop built systems that can respond to the concept of resilience, both in an individual and collective manner. So resilience, the definition of it is, in terms of engineering, is the ability of an organization to anticipate, forecast, manage, and avoid hazards and threats to its primary performance goals. It also resides in the camp of psychology, which is what my master's degree is in, that looks at resilience more in terms of an individual characteristic. In other words, how well does somebody respond to both anticipated and unanticipated hazards within their own life. The commonality between human psychology and built environments is this whole notion of emergence. And emergence is a quality of understanding what the performance outcomes are for something after it's already happened. So this is where computational systems are especially adept at being able to pinpoint or forecast what the potential outcome of a complex system is. So when we look at constructing computational models, we're in addition to the design basis, which are those characteristics that we're either designing or building for, we look at outside design basis and human basis factors. So outside design basis would be those influential factors that are not within the scope of the building owner's requirements or the building standards, and they're often caused by unforeseen or emergent events. So in Florida, we have seen certainly changes to building code requirements due to increasing hazardous weather events. That's something that my license is coming due for renewal, and I have to take a bunch of CEUs on increased wind resistant codes. So those are outside design basis factors, because we know although hurricanes are going to hit, we don't know the extreme results that they're going to cause. So those are outside design basis. Human basis are basically those results that occur due to individual human behavior. So we know that humans can be it can be very difficult to predict how humans are going to respond in a given setting, when all things are normal. Certainly when all things are not normal, humans have a tendency to behave in ways that can be very diverse. And so also part of designing for resilience is understanding the variability of human response in a given environment. So part of the models that modeling approaches that we use consider human factors. And human factors is a concept, again, that resides both within the camps of engineering and within psychology. And it's the discipline that's concerned with the role of humans in complex systems, the design of equipment and facilities for human use, and the development of environments for comfort and safety. So a lot of us in design were introduced to human factors specifically through things like ergonomics, physical ergonomics, how ergonomic is a chair, how ergonomic is a computer station. And that really looks at physical ergonomics in the context of human factors, but human factors also deals with human cognition. In other words, how well does somebody maneuver throughout a space? How safe is a specific construction site? All of those are also dealing with human factors, human capabilities, cognitive demands, incentives, and operational systems. So another aspect of this is really honing in on human cognition and things like working memory, especially with environments now being increasingly built environments being increasingly blurry in terms of what is an actual built environment. With the advent of things like AR and VR and the metaverse, what constitutes an environment, it also changes the way we as humans respond to different things within different environmental typologies. So more and more, I'm not sure why this is doing this, more and more we're seeing things like user experience or UX and cognitive ergonomic support models that were previously just used for things like human-computer interaction, finding their way into built environments and built environment complexity modeling. The benefit of this is understanding what is necessary for users to operate at a higher level of cognitive functioning in increasingly complex environments, and then having environmental design that verifiably supports this will be critical to their success. So as a way of explanation too, oftentimes the terms computer aided and computational design get a little muddied in terms of the understanding of these. So computer-aided design basically uses technologies that create, visualize, and modify the design of a specific space. So oftentimes when we're using things like Revit or AutoCAD, that's computer-aided design, because the concept of the system design resides within the designer's brain. That's something that you're plugging into the system and that the computer is helping you visualize. It's very useful for understanding system design components and the collective of them, and it's helpful for developing plans for design optimization. However, you're not really asking the computer to think for you. That is where computational design comes in. And computational design is basically the process of leveraging that computational intelligence for understanding how the design systems function within a complex operational process. So the concept of the system design is informed by the analytical outcomes of your computational model. The information on design performance generated by computer simulation, and it's also helpful to understanding how a design functions within a complex integrative system. So in terms of using this in a design thinking framework, which is common, especially in the fields of architecture and interior design, which is where I teach, is we can look at using artificial intelligence and computational models within this particular common design thinking framework of empathize. In other words, what problem are you trying to solve? Defining where do I find information about the problem, ideating what methods or computational methods can I use to quantify current state outcomes, prototyping what AI models can I build or use to analyze data and test the effects of interventions and outcomes, and then testing how do I evaluate the accuracy and validity or generalizability of my AI models. So as AI artificial intelligence becomes more integrated in everything from news, we read to the cars we drive and the ways we heat and protect our homes, critical human thinking is more important than ever for the users of these products and designers who create them. So we're becoming acutely aware that things like AI is not just a nice to have tool in our toolbox for design. It's really anymore becoming a need to have as the systems we design become increasingly complex. We can also look at operationalizing what we'd call basically distributed AI and complexity modeling. This is using AI models for looking at complex integrative systems interactions. And that can also follow the design thinking double design model, where we have a problem, we research the problem, we understand the problem definition and causal relationship identification through the computational model, and then the design is informed by that computational model. I can tell you, as someone who started in the early 90s in design, usually when we were designing a complex system, we relied strictly on, again, best practices, building codes, and then heuristics, or in other words, this is the way we've always designed it, and so this is how we're going to continue to design it. That is not usually the best course of action now. Now it's increasingly useful to use computational models to better predict the inferences you have about the outcomes of your design or construction. In terms of looking at this in terms of design programming, we can take a design programming hierarchy and look at the integration of AI through gathering relevant information. In other words, what's the causal relationship between inside and outside design basis factors, as I mentioned before, quantifying the requirements, how does the current system architecture influence dynamic performance outcomes, and then summarizing the problem. What do dynamic scenario simulations tell us about predictive design resilience potential? So we can see something that we've used for decades now, the whole building design programming hierarchy, marries up well with this notion of applied computational design modeling. So where do we usually start when it comes to curriculum development? Usually when we're training students, and we have a lot of introductory courses in this college right now, look at teaching student principles of machine learning. Machine learning is a good on-ramp method for having students be familiar with ways to use applied AI to informing design. So this is an example of what we call supervised machine learning. In other words, I know the data that I'm working with and I understand how they're labeled. So we start with labeled data when you can define the factors you're analyzing and have a clear understanding of the relationship to a potential outcome. Predictive outcome analysis, the goal being to train a model so that it can predict outputs when given new data, and then understanding the data relationships. The supervised learning offers a way to use machine learning to evaluate relationships between input and output variables. So what would this look like? This is an example of an actual research study that we're working on right now at Fiber that looks at the resilience level of community infrastructure to support vulnerable urban community members. So this specifically looks at the paradigm of regional housing quality and accessibility as an indicator of poor community health outcomes. So this is, although a clustering algorithm, and most clustering algorithms are indicative of unsupervised machine learning, this support vector machine is actually supervised learning because we're using labeled data. And so the outcomes of this study suggest that across the state of Florida, poor quality housing, in other words, housing that is has a high housing cost burden, has a low housing quality, has other issues related to housing accessibility to those vulnerable communities, tracks alongside with poor health outcomes like acute and chronic respiratory conditions. So the benefit of understanding this is, especially whether we're talking about design or engaging with policymakers, is that if there was investment in improving housing infrastructure and design, it could contribute to better public health outcomes, because that's what the findings of this are showing, at least within the state of Florida. We can also use this for more discrete examples. This is, for those of you who might not be familiar with it, UF has one of the only well building practicum labs, I think in the world, if certainly in this country, that works with the Institute for Well Building Institute, the International Well Building Institute. And we can also apply things like decision tree algorithms to selecting materials that would meet a sustainability standard metric, which if you take the Well Practicum Lab, you'll learn how to do this. And so this looks at the concept components of the materiality concept for well, and looks at the ability to meet certain degrees of adherence to these, and then selecting outcomes that would best contribute to achieving a well-certified building. So one of the ways that we've done this in a little bit more sophisticated method is some of our lab work at Fiber, looking at material safety as it relates to infection control. So this specifically looks at the key performance indicator variables of materiality robustness, recovery to advanced cleaning procedures in healthcare environments, and sustainability. In other words, material that's free of red list components, which are actual harmful chemicals that are embedded in different types of building materials that could be hazardous to human health, and coming up with a resilience score based on this. This uses adaptive neural fuzzy inference systems, which is a combination of fuzzy logic and neural networks. And the outcomes of this basically show us that if you plug in these characteristics for different types of building materials, it will give you a consistent outcome every time. Again, this is a way of having the machine basically learn from the information that you're inputting in it to have a predictable result. So this was also patented through UF Innovate, and we published an article in the Health, Environments, Research and Design Journal recently on using this. So again, these are good for showing discrete outcomes of specific areas of building design and construction. What do you do when you have a system that is complex and has a variable of time as a component? So one of the systems engineering tools that we're using in some of our research right now is called systems dynamic modeling. And it was created by Jay Forrester, who was an electrical engineer by training and was a professor at MIT. And one of the things that Forrester observed was that in complex systems, cause and effect are often not closely related in time or space. In other words, something that you're designing or building right now might work great for this current state or this population, but as time goes on, as populations change, as needs change, we can see differing results that we didn't necessarily expect. And so this is where complexity modeling in terms of computational modeling is very helpful. Oops. So again, my PhD training is in systems science and systems engineering. And so in that, we do a lot of evaluation and understanding of systems that are generalizable across different paradigms. One of the concepts that we spend a good deal of time studying in systems science is Bertalanffy's general systems theory, which is basically the science of wholeness. So if I'm designing a building, I need to consider more than just the building type. I need to consider the environment that it's existing in. I need to understand what users are using it. I need to understand how the users will change, how certain risks can affect that building in a different way, given a period of time. And so a system intelligent person can understand systemic phenomena and that it changes over time. And they know that most human systems and organizations, the true system often includes hidden subsystems such as processes of fear and trust generation. The inputs, the interventions available usually control both systems, and the challenge is to understand how the inputs be used to activate all the states of the system. So in other words, it's also understanding how to design and build systems that can support varying degrees of human trust and capability and do so relatively successfully, or at least in a balanced way. In terms of achieving this, this can be a very tall order. So there's two main techniques available to designers to test design. One is usability testing, which is very effective for generating feedback loops on design performance. However, it's very expensive and time consuming because you have to outreach to the users, you have to get their opinion. And then again, that can be misleading if you're talking to the wrong people. Another approach is modeling, which basically requires abstracting human performance characteristics to determine systems interaction outcomes, allows for scenario testing to predict what design versions result in the best performance, and is a multifaceted approach to making predictions about users. So one of the quotes I always use when I teach the data science for interior environments class is, all models are wrong, but some are useful. If you look at the map of the world, it's not actually an accurate map of the world because it's a map, right? It's not the size of the entire planet, or it'd be completely accurate. So in understanding this, we can use modeling as a form of abstraction to better understand what the general outcomes are of the predicted system users. So one of the approaches we use in our research is agent-based modeling, which also offers a nice on-ramp to systems dynamic modeling. And agent-based modeling looks at developing computational models of discrete agents within an environment with differing components to it, to see what their self-organizing behavior is. The benefit of this is that if you have a system where you're trying to ensure that it is achieving certain areas of goal-seeking behavior, this gives you a good idea of whether that's happening or not. So the example I have pulled up here is called the wolf-sheep predation model. And it looks at the resource of grass, the resources of sheep feeding the wolves, and wolves predation on the sheep to see what the overall system behavior is. I like to use this as an example for explaining how this is valuable to building, because the grass in and of itself is a resource much the way that built infrastructure would be. So we can see what happens with the resource provision and availability being balanced versus then that changing with some slight alterations to the model. So I have a video that shows this running. Takes a little while to start. So we can see as the model runs, wolves eat the sheep, sheep eat the grass, and we can see over here in this section in terms of population, we have cycles up and down, but the system dynamics are relatively imbalanced. And that's what we like to typically see when we have a system. It's very rare when we have everything be a completely straight line. That's not usually feasible. However, when you change the variable of resource provision in terms of just changing the grass. So if I increase the time it takes for the grass to grow, and then if I also, yeah, I took my time doing this. And then if I also decrease the benefit of that resource to the sheep, we can see what that does to the overall system. So I'll go ahead and set that up and then press go. And so as time goes on, we can see automatically what happens to the wolf population. It completely dies out. Wolves don't eat grass, so that's kind of a surprise, right? But if the net gain to sheep is diminished and sheep are the primary resource for wolf well-being, then the wolves die out. And so then we can see again over time the sheep are kind of hanging on, and then eventually everything dies. So the benefit of understanding this model is when we're looking at resource provision in terms of availability and utility, if we change the accessibility and the utility of that resource, the entire system can suffer in ways that we didn't necessarily predict. So part of this is looking at the dynamics of the system, and dynamics of the system goes back to that box that I showed in the corner of looking at the whole systems. It's that Bertalanffy's general system theory idea of a holistic approach to systems. So one of the ways that I explain this is the bathtub model. As we have a flow of resources in to a repository, how do increases to that or decrements to that change the overall performance level? And so this is basically the structure of a systems dynamic model. We have data flowing into a specific stock, and then we have data flowing out of that stock. And the outside process parameters are what are often either feeding into the system or outside the system. And then there are also temporal variables introduced into this that show, okay, over time, this is what we can expect with our system performance. So if we look at the discrete relationships between factors of these, we have stock factors and a goal-seeking behavior. And then we also have variables that are related to this. So if we take something like temperature, we know that as cooling effects decrease, the temperature goes down. As the temperature increases, the cooling effects go down. That is a balancing loop or reinforcing loop that's negative. As heating effect increases, temperature increases. And then as heating effect decreases, as temperature increases, heating effect increases. That's a reinforcing loop that's positive. So these variable factors influence goal-seeking behavior up and down. Those are things that if we look at an actual built environment, we can introduce designed interventions that can influence this. So an inside design basis factor would be to include a variable that has a cooling power source. So a cooling effect for temperature as cooling goes up, temperature goes down, and as temperature goes up, cooling goes down. That's reinforcing. And then heating effect would be the same thing, but reinforcing positive on both sides. These, again, are internal system design basis variables and generally the things that we can control. However, again, as we were talking, buildings are resistant in relatively complex environments. So part of being successful at design and constructing a building is understanding those exogenous or external system design basis variables. In other words, things you cannot control as well. So in terms of heating, we also need to look at ambient temperature outside, things like climatic changes or the after effects of things like hurricanes or droughts, or if you're on the West Coast of the United States, fires, and then things like urban heat island effect if you're in a city or a suburb. And then in cooling, in terms of extreme weathers, the center photo is actually, I'm originally from Buffalo, New York, and this is a recent picture of Buffalo during their most extreme winter storm. So things like unexpected climatic events that cause the temperature to be very cold, the degree of shading that you might have in an environment, and then obviously precipitation that can cause cooling effects. We know something about this. We can design for this based on the region that we're designing for, but it can be very difficult to predict the extreme natures or the extreme ends of this. So part of understanding this is using a combination of AI and complexity modeling for better understanding the outcomes of this. This is an example of a study that we just recently finished in fiber. This is a model that Arzu actually created using agent-based modeling to track the spread of potential infectious pathogens throughout a healthcare environment. We know that a high degree of infectivity in healthcare environments can cause an increase of infections. However, it's very difficult to predict how this will happen. And so therein lies the benefit of using distributed AI, combination of AI models and agent-based modeling to be able to better predict how this might happen. And so this is an example of one of the latest iterations of this model where we set up the model and let it run. And this is based on just surface and we're C. diff, with Clostridium difficile, to see how pathogens are transmitted throughout this environment. Again, this is a very simplified hypothetical environment, but we can see that this gives us a much better idea about the fact that the spread of infection is not something that we need to specifically just look at the patient rooms or the patient treatment rooms for, but we can see that this exists quite a bit around the clinical workstations as well. We can also see that there's a difference when we look at MRSA, which is a different type of pathogen in terms of its spread and trajectory. For example, we can see that the number of exposed patients increases at a greater rate with the data that we had on MRSA than it does with C. diff. So again, this is specifically constraining this to high touch surfaces that are comprised of things like laminate, but it does give us a better idea about the spread of pathogens in ways that static discrete level predictive models wouldn't be able to. This is an example of systems dynamics that's using the same type of framework, looking at susceptible, infectious, and staff removed from infectivity population from a more whole systems approach, looking at just surface infectivity. So we can see if we run a simulation on this, that we can change certain percent of potential surface infectivity and see how it impacts infectious staff population over time. Again, this is a 8-hour shift that allows us to see to what degree do staff become infectious when we change the degree of infectivity of a surface material. And then we can also change the surface infectivity reduction intervention and see what that does to automatically removing staff from infectivity risk. So again, the benefit of this is it allows us to look at a very complex system, honing in on certain interventions that their integral effect on system outcomes in a way that discrete modeling wouldn't allow us to do. And also heuristics or best practices wouldn't necessarily allow us to be able to forecast the outcomes of this. So in terms of the benefit of using computational design thinking, so the research snapshot of what we're working on right now is we're leveraging advanced technologies to forecast the effects of environment design interventions on system outcomes through computational scenario simulation, to contribute a deeper understanding of risk priorities in human-centered design for environments. And this is to enable planning teams to proactively address environmentally based challenges that impede adaptive response to safety critical demands before design implementation. And so the applications for this are things like risk prevention and prediction. What if planning scenario models? So what will happen if this hurricane hits? What will happen if this pandemic or epidemic hits? And then design resilience forecasting. We're even using this for things like aging in place right now. What is the goodness of fit of a specific type of supportive housing design or a specific type of long-term care design for people aging in place or for accident reduction in older populations. So it's generalizable across a number of different types of applications. We're doing ongoing development for socio-ecological systems analysis for pre-design. That's something that 𝐒𝐏𝐄𝐀𝐊𝐄𝐑 is working on. Algorithms for system risk and design resilience inference, and collaborative design dynamics modeling for decision support. So again, using this as a tool in the toolbox for people in construction design and planning to help inform your own area of domain expertise in planning, design, or construction. So that's all I have. If there's any questions, I'll go ahead and answer them now. Anyone have any questions? No? Okay. Thank you. Okay, thank you. Thank you all for coming. Please help yourself to more pizza. Thank you for those of you online who joined. Sorry for the slides jumping ahead. Yeah, if you have any questions about this, feel free to email me. I'm happy to talk about it more with you. I also teach a graduate level course in data science for interior environments where we go through some of this stuff. And then we're teaching some of our interior undergraduates machine learning as well. But UF has really made a big commitment to using AI. So there's the AI certificate in DCP. I highly recommend that and exploring courses related to that. And then we'll be continuing the DCP research seminar series on February 3rd. So that more information will be forthcoming about that. I encourage you all to join. I don't know if there'll be pizza, but there's liable to be something else good to eat. So feel free to stop by. Okay. Thanks, everyone. Bye. Bye.